So what we're going to do now is we're going to take these line integrals. We're going to work again in vector fields, but we'll get some practice parametrizing curves. And we're going to go through a bunch of different examples and see if we can pick out any kind of properties. So we're going to start with just an example. And this is going to lead to this concept called the fundamental theorem for line integrals. So we're going to consider the vector field f, which has two inputs, x and y, given by y plus 1 and x. We are going to evaluate the line integral over the curve C of f dot dr over each given curve C. So we're not going to change the vector field at all. All we're going to do is change the curve and the starting and ending points. So we're going to start with C being the line segment. From the point 0, 1 to 1, 0. So when you're working with line segments, I'm going to show you a specific way that's very beneficial. So your t-bounds will always be 0 to 1. In reality, yes, you can find the equation of the line, but because here the orientation matters, like the starting and ending point is important. For certain segments, it can be kind of hard if you just find the equation of the line, because your t-bounds will be a little bit weird for it. So with this one, I'm going to go ahead and draw our curve C first. So we're starting at the point 0, 1, which is up here, and going to the point 1, 0. So this is our oriented curve C. So first thing I need to do is I need to find that parameterization of C. So this means I want to find a vector function that guarantees I'm on this curve, and more specifically, it traces the curve in this direction. So what I tend to do is I like to pick that starting point, and then I'm basically finding the distance that I need to travel in both the x and the y. So you turn your starting point into a vector, which is 0, 1. And then we're going to find the distance we need to move in the x and the y direction. And this will be multiplied by t. This is basically finding the slope. So to find the distance, what I'm going to do is I'm going to look at how much I move in the x direction, doing the ending minus the starting value. So in the x, I need to move a distance of 1. And then in the y, I need to move a distance of -1. And the way I find that is doing the ending minus the starting. So this one will be 0 minus 1. Okay, so we can condense this now to a single vector. Looking in the x component, that's 0, and that's 1t. So this would be 0 plus t in the first piece. And then in the second, that's 1, and then minus 1t. So that's 1 minus t in the second component. So the vector curve that defines C, or the vector function that defines C, is t and 1 minus t, and the t values will be between 0 and 1. So the reason this way is nice is because when you plug in 0, that gives you 0, 1, the starting value. Then when I go ahead and plug in 1, that gives me 1, 0, the ending value. And then I go along that curve. So this is my parameterization. Now I want to go ahead and I've got to find its derivative. So r of t is t and 1 minus t. R prime of t is then 1 -1. Then my vector field F is given by y plus 1x. And again, I need to see what does the vector field look like on the curve. So plugging in those pieces, y is 1 minus t. So that's 1 minus t plus 1, and x is t. So this gives me 2 minus t, t. Okay. You can then find the dot product between the vector field and r prime of t. You can jump into the line integral, completely up to you. So if we want to find this line integral, we go ahead and integrate from 0 to 1 of f evaluated at r of t, dot product with r prime of t dt. So that's the integral from 0 to 1. This is 2 minus tt, and then r prime of t is 1, -1. And then we integrate with respect to t. So dot product, we take the first components and times them by each other. So 2 minus t times 1, and then I add t times -1. And thankfully, this is just a nice polynomial. This is 2 minus t minus another t. So this is really the integral from 0 to 1 of 2 minus 2t. So finding that antiderivative, let's go ahead and just do this up here. That gives us 2t minus t squared, evaluated from 0 to 1. Plugging in 1 gives me 2 minus 1. Plugging in 0 gives me nothing. So this overall is equal to 1. So the work I would do along this particular path C in this given vector field is 1. Now for the next one, what I'm going to do is I'm just going to flip this. I'm going to trace it in the opposite direction and see what happens. So example B is C is the line segment from 1, 0 to 0, 1. So we're starting here at 1, 0 and going to 0, 1. We're just tracing it in the opposite direction. And this is where that parametrization is important, because if you were to come up with the equation to this line, it's exactly the same as the last one. However, I cannot use the same parameterization because it traces it in the wrong direction. So instead, what I'm going to do to find my r of t is, again, I take that starting point, 1, 0, and then I need to figure how much I'm moving in each direction and times it by t. So for the x, I'm moving a distance of -1, and then in the y, I'm moving a distance of +1. Again, that's found just by subtracting the x values and subtracting the y values. So my x is ending at 1, starting at 0. Y is ending at 1, starting at 0. So that really gives me 1, 0, and then this is -1, 1, t. So combining these, that gives me 1 minus t in my first component, and then 0 plus t in the second. And again, I'm able to use that t is between 0 and 1. Just show you, if you plug in 0, that gives you 1, 0, which is exactly right here. And then when you plug in 1, that gives me 0, 1. So then I end at this point. So it traces it in the opposite direction. All right. So so we're doing good. Now we can find r prime of t. Okay, let's start by just rewriting r of t down here because I need to evaluate the function at this. So r prime is going to be negative 1, 1. Our vector field is y plus 1x. So my vector field on this curve, well, my y is t, and my x is 1 minus t. So this time I'm going to go ahead and I'm going to do the dot product between these already, so I don't have to do it inside the integral. You're going to take t plus 1, 1 minus t, and dot product it with negative 1, 1. So this gives me negative 1 times t plus 1, and then 1 times 1 minus t. Gives me negative t minus 1 plus 1 minus t. So at least this cleans up a little nicely. The minuses cancel, and this becomes negative 2t. So the line integral over this particular curve is then going to be the integral from 0 to 1 of negative 2t dt, which is just negative t squared evaluated from 0 to 1. So we end up with negative 1. Okay. So if I can compare these two, I had positive 1 for this direction, negative 1 for this direction, and all I did was trace the curve in the opposite orientation. This is always going to happen. So just as a little note in general, if you're taking the line integral over c of f dot dr, and you take the line integral of negative c, indicating it's the opposite direction, these will always be opposite signs. So it's the opposite of this one. Okay. So this is where negative c is the curve with opposite orientation. Of the curve C. Okay. So these two will always just differ in sign. All right, let's try a third one. And I'll do one more with this one. Okay. This next one's going to be a little bit more annoying. So instead here, C is the piecewise smooth curve. Comprised of the line segment from 0, 0 to 1, 0, and the line segment from 1, 0 to 0, 1. So first thing I'm going to do is I'm going to draw what this curve looks like. So first I'm going from 0, 0 to 1, 0. And I'm moving in this direction. And then second, I'm going from here up to 0, 1. So if I'm going along this curve, there's no way I can parametrize this with a single thing. Instead, I'm going to have to break it down into two pieces. So this bottom is C1, and then this piece is C2. And thankfully, we've already done C2. Okay. So if I want to find the line integral over this whole curve, I'm going to break it down and find the line integral over C1. And then I'm going to add the line integral over C2. Now the problem is I don't want to use the same R here because these are going to be two different vector functions to describe each of these curves. But again, this one I've already done. This is exactly that second example. So we already know what this equals. We don't need to go through this. This is equal to -1 from part B. So instead, I just have to go through what does the line integral over C1 equal. So we've got to find that parameterization of C1. So again, because you typically would have to do two different vector functions, this one I would call R1 of t. I don't want to use R because I have two separate functions. So here we're starting at 0, 0. And then for the x component, that's 1 minus 0. So ending value is 1, starting value is 0. And thankfully in the y, we're not going to move at all. It's 0 minus 0. So this is really equal to t, 0. And then our t is ranging between 0 and 1. So we've got our vector function. We also need its derivative, which is nice. That's just 1, 0. As a reminder, for our vector field, this is y plus 1x. So plugging in this particular segment, our y is nothing. So this gives us 1 and then t. Okay. So again, going to take the dot product of these two so I don't have as much going on. We're going to dot product this with R1 prime. That gives me 1t dot product with 1, 0. And luckily this is really nice. This is just 1 plus 0. So this is a fantastic thing to go inside of our integral. So that tells me the line integral over the curve C1 of f dot dr is the integral from 0 to 1 of, again, the dot product of these two things. So I'm integrating 1 from 0 to 1, which gives me t evaluated from 0 to 1. So overall, this equals 1. So in total then, over the entire curve C, we take the line integral over C1 based on the curve that defines that, and then the line integral over C2 based on the R that defines that one. First integral we just found it as 1. From the last example, that second line integral is -1. So overall, this line integral is equal to 0. Okay? So we're going to do one last more example with this vector field. Here, C is the line segment from 0, 0 to 0, 1. So in this case, we're starting here and ending here and going in this direction. So if you notice in comparison to this last one, it's less complicated, but it still has the same starting and ending point. and that's going to be important for us. So let's go ahead and find the parameterization of this curve. Again, you can use the same idea. We're starting at 0, 0. In the x direction, we're not moving at all. In the y direction, we're moving a distance of 1. So this can be defined by 0t, with t ranging between 0 and 1. So then the derivative of this is 0, 1. And at this point, I'm not going to bother copying down the vector field again. If we evaluate f on this curve, that is y plus 1. So this is t plus 1. And then x, which is 0. So to find the line integral over c of f dot dr, it's equal to the integral from 0 to 1 of t plus 1, 0, dot product with 0, 1. And then really what happens is the first component's multiplied to 0, the second multiplied to 0, and when you integrate 0, it gives you nothing, which is exactly what we got in the last section. Okay. Realistically, what could happen is I could pick another path with these same starting values, and maybe instead you take like a circle between those. No matter the path we actually picked for this particular problem, this line integral will always equal 0 when it has these particular starting and ending points. Okay. So no matter the path we choose, from 0, 0 to 0, 1, we will get that the line integral over that curve of f dot dr equals 0. Okay. But this only is because this vector field on the inside. So it is specifically because of this being our vector field. So what I want to do is I want to then naturally ask, well, is this always going to happen? So what happens if we use a different vector field? So let's try it out with 2 examples. Let's let the vector field f be given by y, 0. We're going to evaluate the line integral over the curve of f dot dr, where first C is the line segment, from 0, 0 to 0, 1. So I'm going to make it somewhat nicer in that we don't have to come up with the parameterizations on these because we're going to take the same pass. So in this case, we're starting at 0, 0, going to 0, 1. This is exactly that last example. So the vector function that defines this curve is 0t, where t ranges between 0 and 1. And then r prime of t is 0, 1. Our vector field in this case on the curve is going to look different. So the first component is y, so that becomes t. And then the second component is 0. So the line integral is then going to be the integral from 0 to 1 of the function on the vector field dot product with the derivative. So this gives us the integral from 0 to 1 of 0, which does lead us to exactly the same answer. Okay. But now let's go to the same path we have back up here, where it's this piecewise segment. And we're going to see, do I get 0 in this case as well? So the second one we're going to calculate is where C is the piecewise smooth curve. Comprised of the line segment from 0, 0 to 1, 0. And then the line segment from 1, 0 to 0, 1. So giving that picture, we're starting out at 0, 0 and then to 1, 0. I'm going to call this curve C1. And then going from there up to 0, 1. So this is C2. We've already gone through the parameterization for both of these. So C1, we can use the vector function R1 of t, which is given by T0, for t being between 0 and 1. For C2, we use the vector function R2 of t, which is given by 1 minus t, t. And then t is trapped between the same bounds. So all you're going to do is look in the first example. To get these. Okay? So we'll start by finding the line integral over C1. So I'm going to go ahead and label. This is going to be for C1. The vector function R1 is T0. So its derivative is 1, 0. The vector field F is Y0. So F along this particular curve is just going to be 0, 0, which is fantastic. So the line integral over C1 of f dot dr1 is the integral from 0 to 1 of 0, 0 dot product with 1, 0. But that's just 0 on the inside. So this line integral is equal to nothing. Going along C2 instead, the vector function R2 is 1 minus tt, and its derivative is negative 1, 1. And then we already have the vector field above, so I'm going to evaluate this on the curve. The y component is t. The x component is always 0. So the line integral along C2 of f dot dr2, the integral from 0 to 1 of t0 dot product with negative 1, 1, integrated with respect to t. that really just gives us negative t plus nothing, which the antiderivative of that is negative a half t squared, evaluated from 0 to 1. So this line integral is equal to negative 1/2. So when I want this total line integral, because it's this piecewise smooth curve, I go ahead and add these two together. So overall, the line integral over C of f dot dr is the line integral over C1 with that parameterization for the vector function, plus the line integral over C2 with that parameterization. First one we found is 0, second we found is a half and negative. So overall this is equal to negative a half, which is not what we got for this path, which still had the same starting and ending values. We found this one overall equaled 0, but same starting and ending values, different path, led us to an answer of negative 1/2. Okay. So here, the line integral over the curve C of f dot dr is independent of path when the vector field on the inside is y plus 1x, but it is not independent of path when the vector field was changed to y 0. Okay. So the path did not matter for the first example, but it did matter in the second. So we want to figure out what is so special about that first vector field. And this is where that concept of conservative vector fields comes into play, because this is finding the work. So if I have a conservative vector field, all that's going to matter is the starting and ending point, because energy is going to be conserved overall. If it's not conservative, then the path you take is going to matter, because there's going to be a path of more resistance or a path of least resistance. But with a conservative vector field, it will not make a difference. So basically, if you remember what that means, a vector field's conservative if this is the gradient vector of a function. So that basically means I can find a function whose partial derivatives are this. But this is not conservative, meaning I cannot find a function whose partial with respect to x is y and partial with respect to y is 0. Okay? So this is tying in pretty much a lot of our stuff together. If you remember, we talked about mixed partials way back when, and if you started with a function, you automatically knew that the mixed partials were going to be equal. However, here, what I'm saying is these are the partial derivatives. If that's the case, the mixed partials better than be equal. And same thing here, if these are representing the partial with respect to x and the partial with respect to y, the mixed partials for this one should be equal. If that's true, then I'm guaranteed I can find a function that has this as the partial with respect to x and this as the partial with respect to y. So what we're going to do is just kind of summarize all of that, and then we'll also talk about how do I then find the function if these are its partial derivatives. Okay, so putting everything now into words on paper, let's let the vector field f be comprised of functions p and q. This is going to be very common notation. So the first function is p, the second function is q. Recall that we say f is conservative if and only if there exists a potential function little f such that this vector field is the gradient vector of this function. So the first component is the partial with respect to x of the function. The second is the partial with respect to y. So ultimately, if the vector field f is conservative, then these components, p and q, represent these partial derivatives. Okay. So basically, the first component is the partial with respect to x, and the second component is the partial with respect to y. Okay. If I have a nice function, the mixed partials should be equal to each other. So the way I'm going to test if something is conservative is, since this first component is the partial with respect to x, I'm going to differentiate it with respect to y to get the mixed partial. This is the partial with respect to y, so I differentiate it with respect to x, the opposite variable, to get the mixed one. And if you have a nice function, those partials should be equal to each other. Okay. So if p and q have continuous first order partial derivatives, then p is in the first component. I differentiate it with respect to y to get this mixed partial. And q is in the second component. I differentiate it with respect to x to get the other mixed partial. Okay. So in order for f to be conservative, these mixed partials should equal. So what that means is p sub y should equal the partial of q with respect to x. So we're going to show for these two vector fields, the first one, that's true, the mixed partials are equal. For the second one, it's not true. So for A, we're going to let f of x be that first vector field, f of xy, which is y plus 1 x. So again, this is p and q. Okay. So this would be the partial with respect to x. This would be the partial with respect to y. So then, if I take the derivative of the first component with respect to y, well, that would equal 1. So the derivative of this with respect to y is 1. This is in the second component, so I differentiate with respect to x instead. The derivative of this with respect to x is 1. Okay. So these two are equal. This again is representing this partial. This is representing this partial. The mixed partials are the same, so this vector field is conservative. So it means I can find a function who has these partial derivatives because then the second mixed partials are going to be equal. But if we do the same thing for the second vector field, again, what I hope is this is the partial with respect to x, and this is the partial with respect to y. So this is why I don't label it as f sub x, because you aren't guaranteed that it is actually equal to that. But if I take the derivative of the first one with respect to y, it's 1. The derivative of the second component with respect to x is 0. So what this would be saying is that this mixed partial is not the same as this mixed partial. They're not equal to each other. So I cannot say that these are representing those mixed or those first partial derivatives. So there is no function whose partial with respect to x is y and partial with respect to y is 0. So since these two are not equal, we have f is not conservative. There is no function f so that the gradient of f will equal this vector field. Okay? So I'm only going to get the independent of path when my vector field is conservative. And then in that case, you could walk the most complicated path that you want, but really all that's going to matter is the starting and ending value. So in the fact that you have a conservative vector field, it's actually going to be really nice to evaluate. You just need to find this potential function, and you're going to plug in the starting and ending point. So in general, when you find a line integral over a vector field, this is independent of path, so the path doesn't matter. When the vector field is conservative. Okay. So make life a lot easier. We don't have to go through and parameterize any curve. We just find this potential function. So this is exactly what the fundamental theorem of line integrals tells you. It's kind of like when you find the fundamental theorem of calculus, you find that antiderivative and plug in the starting and ending value. Same kind of idea here. You're finding the antiderivative in a sense now of a multivariable function and using those starting and ending points. So let's go ahead and go through the fundamental theorem of line integrals. So let's let C be a smooth curve defined by the function r, which depends on t, and then t varies between the values a and b. We're going to let f be a continuous function such that the vector field is the gradient of f. And this is continuous on C. Then, if you want to find the line integral over this vector field, it is the same thing as finding the line integral over that gradient vector. Okay. Instead of parametrizing the curve, all we're going to do is find the potential function. We're going to evaluate this at the ending point and subtract the potential function at the initial point. Okay. So this will be the initial or the terminal point or ending, and this will be the initial point that we start at. The way you actually find that is by the curve, because it might not tell you starting here and ending here. What you would do to find the terminal point is plug in b into this vector field or into this vector function, and that gives you the coordinates for that ending point. So this is r of b, whatever those coordinates are. And then likewise, to find the starting point, you plug a into the vector function, if that's what's given to you. In our example, it told us the line segment from here to here, so we had the starting and ending points. Okay. Now what I'm going to do is I'm actually going to prove this one because it's not too bad. It's a nice application of our chain rule. So we can go through this pretty quickly. So the line integral over C of f dot dr is again then written as the gradient of f dot dr, which, spelling that out even more, dr is r prime of t dt. Okay. So we're going to do this for a triple. Say we have f as a vector field in 3 dimensions, because that's the most general case that we're considering, because 2D is simpler. So in R3, for the vector function r of t being defined by x of t, y of t, z of t, where t is ranging from a to b, we get that this line integral is equal to the integral from a to b. We're going to take that gradient vector, which is the partial with respect to x, partial with respect to y, partial with respect to z, and dot product it with r prime, which is x prime of t, y prime of t, z prime of t, integrated with respect to t. So this is that first piece, and then this is that second piece. Well, all I'm going to do is write this in a different notation. This is the partial of f with respect to x. the partial of f with respect to y, partial of f with respect to z. And then these are all single variable derivatives. So this is dx dt, dy dt, dz dt. So going through the dot product, we multiply the first components. That's a partial of f with respect to x, dx dt, plus the partial of f with respect to y, dy dt, and the partial of f with respect to z, dz dt, integrated with respect to t. And realistically, hopefully this looks pretty familiar, but this is exactly that chain rule. The idea behind this one is you have this starting function f depending on x, y, and z. So that first row is all partials, and then each of these depend on t. So this next step we get just from chain rule. This is the derivative with respect to t of f. It's f of x, y, z, but all of those really depend on t. So we can write it like this. And then if you think you're integrating the derivative, those two just cancel each other out, so you end up with the function on the inside. Evaluated from A to B. So this really gives you f of x of b, y of b, z of b, minus f of x evaluated at A, y evaluated at A, z evaluated at A. And those are exactly the coordinates corresponding to plugging A and B into the vector function R. So this is R of B on the inside minus R of A. Okay. So that's the proof of our fundamental theorem of line integrals. So what I'm going to do is I'm going to show you with, again, that same vector field that we know is conservative. What I'm going to do is find this potential function so we can get some practice with that, and then utilize that then for that curve from 0, 0 to 0, 1. And we should know that it already does equal 0. Okay. So for our last example, we're going to let the vector field be the one we know is conservative. So we're going to let f be y plus 1x, which we know is conservative, or we've shown is conservative. Not we've, which we've shown. Okay. So what that means is there exists a function f such that this vector field is the gradient vector of some function. Okay. So I can say that this first piece is the partial with respect to x, and the second piece is the partial with respect to y. Okay. You got to be careful with doing these because we're going to take antiderivatives with respect to one of the variables, but you have to be careful of getting that plus c at the end, which we know normally happens. Here, because I'm working with a multivariable function, some other stuff ends up happening. So what I'm going to do to try to find my function is, if I want this, I can go ahead and integrate the partial derivative with respect to x. Okay. So if I integrate y plus 1 with respect to x, that's finding the antiderivative. Okay. So if you think about that, the inside is really just a constant with respect to x. So it's like you're integrating 1 overall. You just get an x attached to it. You can check derivative of this with respect to x is, well, that derivative is 1, so you just get y plus 1. Now, typically what you're used to doing is getting a plus c. The problem is here, I don't quite get that. Instead, I get a function dealing with the other variable. Because if I go ahead now and differentiate this with respect to x, this derivative is y plus 1. The derivative of this with respect to x will be 0. So it gives me an accurate statement. So here, when we differentiate a function of y, with respect to x, this would be 0. Okay. So basically what I've done is I've used this first component. I'm going to use the second component to try to figure out what does this equal. So we need to find this function h of y. By using that the partial with respect to y is just x. Okay. So the function I found here is xy plus 1 plus h of y, which I'll distribute out xy plus x. Okay. So if I take the derivative of this with respect to y, that gives me x plus 0, and then the derivative of this is h of y. So these two better equal each other. So essentially, I'm pairing things up and seeing, do I have anything that's missing or left over? So if I set these two equal to each other, that tells me x plus h prime of y is exactly equal to x. So since I don't have, say, like a plus 7 over here, if I did, that told me h of y would equal 7. But in this case, if I match the two sides, it's going to force this to equal 0. Okay. So if I need to find this function, this is now a Calc 1 problem. We go ahead and integrate this with respect to y. So we end up with a constant. We use k because, well, we've used c already to define the curve c. Okay, so this is a constant. Okay. So our potential function is xy plus x plus k. This is the most general potential function. For the vector field y plus 1 x. Okay. And you can check that you did find the correct thing. If you go ahead and take the gradient of f, the partial of this with respect to x would be y plus 1. And then the partial with respect to y will be x. So indeed, we found the right potential function. Okay. But now I can go ahead and just show that any curve through the point 0, 0 to 0, 1 is going to give the same line integral. So using our fundamental theorem of calculus or line integrals now. So let's consider the line integral over f, which is y plus 1x, where c is any piecewise smooth curve from 0, 0 to 0, 1. Then the line integral over any curve is just going to be this potential function at the ending point minus the potential function at the initial point. And you don't have to worry about the plus k in this case because it's the same thing when we do just a basic integral. You can pick k to be 0. So our function is xy plus x. So if I plug in 0, 1, that gives me 0 times 1 plus 0. And then if I plug in 0, 0, 0 times 0 plus 0, this is overall equal 0. So this confirms our results from the first example. Okay. All right. So I know this is probably a pretty long video at this point. I will link another video just on finding some potential functions so you can see more examples, especially in this kind of case here where you don't necessarily have that this derivative is 0. The one key piece of advice I have for these problems is if it tells you, especially any piecewise function, that's a clear indication that this is likely a conservative vector field. So don't sit there and try to parameterize or come up with a curve. Instead, find this potential function. Also, if you're given like a problem where you have to do 3 or 4 line integrals that have the same starting and ending point, it's pretty simple just to check if the vector field is conservative. So it can save you a ton of work with that. And even if it's not the same starting and ending point, checking that it's conservative when you have to calculate like 6 line integrals for the same vector field will help you save time because then you just go ahead and use the starting and ending points. You have to find that function once and then you just utilize it a bunch of times. Okay, so again, I will post another video just on finding potential functions, but again, don't want this to be a 3-hour long video for you.